Hi Year 12, this is our third lesson for the topic of proof. In this lesson we're going to look at indirect proof. So in our first lesson we looked at logic, the language and notation of proof, and process. And last lesson we looked at existence and counterexample and direct proof. So we're going to look at two types of indirect proof, proof by contradiction and proof by contrapositive. So let's begin with proof by contradiction. This involves us assuming that the statement to be proved is false, which is then going to lead to an absurd conclusion. And this will mean that we were wrong to assume the statement was false in the first place, and that in fact it must be true. Here's an example. For all positive integers a, if a is even, then a squared is even. Now we're going to look at the negation of that. Suppose a is even, but a squared is odd. So if a is even, we can write it as 2m, where m is an integer. And so a squared would be equal to 2m all squared, which is 4m squared, which is even. And this leads to an absurdity or contradiction because a squared is both even and odd. Therefore, by contradiction, if a is even, then a squared is even. Now, the most common proof by contradiction is proving that numbers are irrational. Here's an example. Prove that root 2 is irrational, and we're going to start by assuming that it's not irrational, or in other words, that it's rational. If it's rational, it means we can write it in the form a over b, where a and b are integers, b is not equal to 0, and this part's really important. A over b is irreducible. That means it can't be simplified. You could also say that a and b are co-prime. In other words, they only have one common factor, and that's 1. So we can say square root of 2 is equal to a over b. Squaring both sides, we get 2 is equal to a squared over b squared. And bringing the b squared up, we get 2b squared is equal to a squared. And so we can say that a squared is even. And by extension, a is even. Therefore, we can write a as 2m, where m is an integer. And substituting that back in, we get 2b squared is equal to 2m all squared, which is equal to 4m squared. And dividing both sides by 2, we get b squared is equal to 2m squared, which tells us that b squared is also even, and by extension, b is even, which brings us to our contradiction, because both a and b are even, which means that a over b is reducible. A and b have a common factor of 2. Therefore, root 2 is irrational. And we also need to be able to do this for log questions. Prove that log base 2 of 5 is irrational. We'll start by supposing that it is rational. Therefore, it can be written in the form a over b, where a and b are integers and b is not equal to 0. With the log questions, it's not so important that a over b be irreducible. You can put it in if you want to, though. So therefore, log base 2 of 5 is equal to a over b, and now I'm going to take that out into index form. So this is 2 to the power of a over b is equal to 5, and then raising both sides to the power of b, I end up with 2 to the power of a equals 5 to the power of b, which actually brings us to our contradiction, because no number can be both even and odd. Can you see that? Furthermore, this breaks the fundamental law of arithmetic, which states that every number has a unique prime factorization. Now, do you remember back in Year 7 where you did factor trees? You took a number and you factored it 2 and 6, and then 2 and 3, and you could write it as a product of its prime factors. Does it ring any bells? There is a unique prime factorization for every number. So there is no number that can be written as 2 to the power of something and also as 5 to the power of something. So that's the fundamental law of arithmetic. Anyway, either way, log base 2 of 5 is irrational. We can also use proof by contradiction with geometrical proofs. Prove that the angle between a radius and a tangent is a right angle. So we'll start by assuming that angle OBC is not right angled. Therefore, there must be a point D on the tangent where ODC is a right angle, and it can be either this side or this side, it doesn't really matter. Now we're going to look at this triangle here. If triangle ODB is right angled at D, then OB must be the hypotenuse, because the hypotenuse is opposite the right angle. But here's our contradiction. This is an absurdity since OD must be longer than the radius of the circle. Therefore, the angle between a radius and a tangent is a right angle. Okay, let's move on to proof by contraposition. Now remember, the contrapositive statement is logically equivalent to the statement itself. So if we prove the contrapositive statement is true, then it follows that the statement itself must be true. Remember, the contrapositive statement of P implies Q is not Q implies not P. Here's a numerical example. For all integers x, if x squared take away 6x plus 5 is even, then x is odd. Now this would be very difficult to do via direct proof. We'd have to take this expression and put it equal to 2m, where m is an integer, and then try and solve for x. We'd end up in all sorts of trouble. But by contraposition, it's actually quite easy. I'm going to start by letting P be the statement that x squared take away 6x plus 5 is even, and Q be the statement that x is odd. The contrapositive statement is not Q implies not P. Or in other words, if x is even, then x squared take away 6x plus 5 is odd. Now it's straightforward from here. If x is even, we can write it as 2m, where m is an integer. Substituting it in here, we end up with 2m all squared, take away 6 lots of 2m plus 5, and expanding that out, we can see that it's odd. Consequently, x squared take away 6x plus 5 is odd, so we've proven the contrapositive statement. Therefore, by contraposition, if x squared takes 6x plus 5 is even, then x is odd. Here's another example. If a square number is divisible by 3, show that its square root is also divisible by 3. Now this is quite difficult to do as a direct proof. It would involve us saying x squared is equal to, say, 3m, where m is an integer. And then we'd have to take the square root of both sides. And it's going to get ugly very quickly, isn't it? But by contraposition, it's quite easy. Here's the contrapositive statement. If a number is not divisible by 3, then its square is not divisible by 3. So let's start. Assume a number n is not divisible by 3. There are two cases. It has a remainder of 1 or it has a remainder of 2, and we need to prove both of those. Here's case 1. Let n equal 3k plus 1, and we want to prove that n squared is not divisible by 3. So substituting it in and expanding it out, it's not divisible by 3. In case 2, n equals 3k plus 2. Again, we want to prove that n squared is not divisible by 3, so substituting it in and expanding it out, we can see it is not divisible by 3. So therefore, if a number is not divisible by 3, then its square is not divisible by 3. And so, if a square number is divisible by 3, then its square root is divisible by 3. So which method is best? Well, with numerical proofs, contradiction and contrapositive can be very useful, particularly with square roots, proofs involving infinity or irrationality. With geometrical proofs, often direct proof is easiest. And there can be multiple ways to prove a statement. It's good to know how to complete a proof in different ways, because sometimes you'll be told the method that you have to use. And also, some proofs involve multiple methods. Did you see that last example where we had proof by contraposition that also involved cases? All right, our next lesson is on inequality proofs.